Just after sunrise, a convoy of mining trucks crawls across a stretch of northern Chile where almost nothing else moves. Their headlights cut through a landscape so dry that some weather stations nearby have gone years without recording measurable rainfall. Dust rises behind the tires, but it is not ordinary dust. It is ground that has remained almost unchanged for millions of years, preserving chemical traces that rain would have erased almost anywhere else on Earth. The drivers know exactly where they are going because there are few landmarks left to follow. From a distance, the desert appears lifeless. Yet beneath its surface lies one of the most valuable environments on the planet and one of the most unforgiving. This is the Atacama Desert, widely recognized as the driest non-polar desert on Earth. It stretches for hundreds of miles along the Pacific coast of South America, trapped between the Andes Mountains to the east and the Chilean Coast Range to the west. Those barriers do far more than shape the landscape. Together they create a natural prison for moisture. Air arriving from the Pacific is cooled by the Humboldt Current before it can carry significant water inland. Whatever moisture survives is blocked again by the mountains. Clouds often appear overhead, but many never produce rain. They simply drift away, leaving the ground untouched. At first glance, the Atacama looks empty. That illusion has fooled travelers for centuries. Early explorers often described endless fields of rock and salt, where even insects seemed absent. But the true danger of this desert has never been its silence. It is the invisible systems that make survival possible, and the astonishing speed with which those systems fail. Unlike deserts where temperatures alone threaten human life, the Atacama attacks through scarcity. Water disappears almost as soon as it arrives. Organic material decomposes at an unusually slow pace because microbes struggle to survive in the extreme dryness. Some valleys have remained so unchanged that scientists compare parts of the landscape to the surface of Mars. Space agencies have repeatedly tested robotic equipment here before sending missions millions of miles away, because few places on Earth offer conditions so hostile to life. Yet despite this reputation, people never stopped coming. The reason is hidden beneath the desert floor. During the 19th century, prospectors realized these barren plains contained enormous deposits of sodium nitrate, a mineral that would become one of the world's most valuable resources. Before synthetic fertilizers existed, natural nitrate transformed agriculture. It also became essential for manufacturing explosives. Suddenly, one of Earth's most inhospitable environments became the center of a global economic race. Entire towns appeared where almost no natural water existed. Thousands of workers crossed into a landscape that could not support them on its own. Every meal, every building material, every piece of machinery, and almost every drop of drinking water had to arrive from somewhere else. The desert itself produced wealth, but almost nothing required to keep human beings alive. That contradiction created an invisible machine stretching far beyond Chile. Railroads pushed across terrain that engineers once considered impossible. Ports expanded along the Pacific coast to move millions of tons of minerals overseas. Financial markets in Europe depended on shipments, leaving these isolated mines on schedule. Farmers thousands of miles away unknowingly relied on resources extracted from one of the driest places on Earth. The desert was no longer isolated. It had quietly become connected to the global economy. Then everything changed. In the early 20th century, scientists developed a method for producing synthetic ammonia on an industrial scale. The Haber-Bosch process dramatically reduced dependence on natural nitrate. Almost overnight, entire mining communities across the Atacama lost the economic foundation that had justified their existence. Prosperous settlements emptied, schools closed, rail stations became silent. Buildings designed for thousands of workers were abandoned to one of the harshest climates on the planet. Most abandoned cities slowly disappear beneath vegetation, weather, or redevelopment. The Atacama offered none of those endings. Its dryness preserved entire ghost towns with remarkable precision. Wooden structures remained standing. Rusted machinery stayed where workers left it. Household objects survived inside abandoned homes because almost nothing existed to destroy them. Places like Humberstone and Santa Laura became frozen records of an economic collapse that reshaped lives across an entire region. But those ghost towns reveal something far more important than forgotten history. They expose the first hidden rule of the Atacama: nothing survives here by itself. Every successful settlement has depended on systems built far beyond the desert's boundaries. Every industry has required outside support. Every person has relied on fragile supply chains that can disappear faster than the landscape itself changes. That dependency still exists today. Only now, the resource drawing the world's attention is no longer nitrate. It is something even more valuable in the 21st century. Today, the mineral hidden beneath the Atacama is not used to fertilize fields or manufacture explosives. It powers smartphones, laptops, satellites, and electric vehicles. Beneath the vast salt flats of northern Chile lies one of the world's largest reserves of lithium, a metal that has become central to the global transition away from fossil fuels. Once again, an environment that appears almost empty has become one of the most strategically important places on Earth. And once again, its greatest challenge is not extracting wealth. It is finding enough water to make that extraction possible. The Salar de Atacama looks like a frozen sea stretching toward distant volcanoes. The surface is covered by a thick crust of salt that cracks into endless geometric patterns. Underneath lies an enormous underground reservoir of highly concentrated brine containing dissolved lithium. Mining companies pump this brine into massive evaporation ponds, where months of intense sunlight gradually remove the water, leaving behind increasingly concentrated minerals. The process depends on one resource the desert almost never produces naturally. Every ton of lithium extracted changes the balance of one of the driest hydrological systems on Earth. That balance has become one of the most closely watched environmental questions in South America. Scientists continue studying how groundwater moves beneath the salt flats because the system is far more complex than it appears from the surface. Freshwater descending from snowmelt high in the Andes eventually mixes with ancient underground brines that have accumulated over thousands of years. Small changes in one part of the basin can influence wetlands many miles away, affecting flamingos, microorganisms, and plant species that survive only because hidden water continues moving beneath the desert floor. Those wetlands seem insignificant when viewed on a map. In reality, they function like isolated islands of life. A few natural springs create entire ecosystems surrounded by hundreds of miles of extreme dryness. Flamingos gather there to feed on microscopic organisms that flourish in highly saline water. Native communities have depended on these rare freshwater sources for generations, developing settlements wherever groundwater reaches the surface. Outside these isolated pockets, survival quickly becomes uncertain. The Atacama reveals another paradox. Life is not distributed across the desert. It is compressed into tiny, fragile refuges connected by underground water that cannot be seen from above. If one spring weakens, the consequences spread far beyond a single location. Researchers monitoring the region have found that understanding these underground connections is extraordinarily difficult. Water may spend decades, or even centuries, moving through volcanic rock before emerging at the surface. By the time changes become visible, the process that caused them may have started years earlier. Unlike rivers, these hidden systems cannot be observed directly. They must be reconstructed from geological evidence, satellite measurements, chemical analysis, and long-term monitoring. Yet even water is only one part of the equation. The Atacama is also one of the clearest windows into space ever discovered on Earth. As darkness falls, another invisible system begins to dominate the desert. High altitude, extremely dry air, and remarkably stable atmospheric conditions create some of the best astronomical observing sites anywhere on the planet. Facilities such as the Atacama Large Millimeter/Submillimeter Array, known as ALMA, were not built here because the desert is convenient. They were built because there are very few other places on Earth capable of revealing signals that never survive more humid skies. The same conditions that make human survival so difficult allow scientists to study galaxies billions of light years away. The desert that appears empty by day becomes one of humanity's most powerful observatories by night. That transformation reveals another hidden truth. The Atacama is valuable not because of what stands on its surface, but because of what its extreme environment makes possible. And every one of those possibilities depends on a fragile balance that has existed for thousands of years, a balance that modern demand is beginning to test in ways the desert has never experienced before. Long before lithium transformed the Atacama into one of the world's most valuable landscapes, another mystery convinced scientists that this desert was unlike any other place on Earth. In several regions, researchers searching for microscopic life found almost nothing. Soil samples that appeared ordinary under the naked eye contained microbial populations so small that early testing equipment sometimes failed to detect them at all. For biologists, this was astonishing. Even Antarctica, Often considered one of the harshest environments on the planet, supports more biological activity in many locations than parts of the Atacama. The desert was not simply dry. In certain places, it had crossed a threshold where life itself struggled to maintain a foothold. That discovery immediately attracted another community: astrobiologists. If scientists hoped to understand how life might survive on Mars, they first needed to identify the closest environment available on Earth. The Atacama became one of the leading natural laboratories for answering that question. Research teams began testing drilling equipment, life detection instruments, and robotic technologies across its barren plains. They were not searching for extraterrestrial organisms beneath the Chilean desert. They were asking whether future missions could distinguish between a planet that never supported life and one where only microscopic traces remained. The answer proved far more difficult than expected. Microbial colonies did exist, but they survived in astonishingly isolated pockets. Some occupied tiny fractures inside translucent rocks where enough light penetrated for photosynthesis while the surrounding stone reduced water loss. Others remained dormant for years, becoming active only after extremely rare moisture events. Survival depended not on the strength of the organisms themselves, but on finding microscopic refuges where environmental conditions shifted by only a few degrees or retained a fraction more humidity than the surrounding landscape. Once again, the Atacama revealed the same pattern. Life persisted only because hidden systems created opportunities invisible to casual observation. That lesson extends far beyond biology. Weather forecasts suggest clear skies across much of the Atacama on most days of the year, but clear skies do not mean stable conditions. Along portions of the Pacific coast, dense banks of fog regularly drift inland. Locally known as camanchaca, this fog forms when cool ocean air encounters warmer air above it. Rain rarely follows, yet the moisture suspended inside these clouds has sustained both natural ecosystems and human communities for centuries. In several remote settlements, large mesh collectors are stretched across hillsides facing the ocean. As fog passes through the fine fibers, tiny droplets gather, merge, and slowly flow into storage tanks. No pumps lift water from underground. No rivers feed these systems. Drinking water simply condenses out of the air. It seems almost impossible. One of the driest deserts on Earth can produce water without rain, but only under very specific conditions. If prevailing winds change, if temperatures shift, or if the fog arrives less frequently, the entire system weakens. Researchers continue studying how climate change may influence these coastal fog patterns because even small atmospheric changes could affect communities and ecosystems that depend on them. Farther inland, another invisible force shapes the desert every single day. The Andes Mountains receive snowfall during the winter months, storing water high above the Atacama in glaciers and seasonal snowfields. As temperatures rise, a portion of that frozen reserve gradually melts, feeding rivers that descend toward the desert basin. Without those distant mountain systems, many of the valleys supporting agriculture and human settlements would simply disappear. The remarkable irony is that the Atacama's survival depends on water that often falls hundreds of miles away and thousands of feet higher in elevation. The desert does not create its own lifelines. It borrows them. Every spring, every oasis, every productive valley reflects processes taking place far beyond the horizon. When snowfall declines in the Andes after unusually warm years, the effects eventually ripple across northern Chile. Farmers notice reduced stream flow. Reservoir levels fall. Competition for groundwater intensifies. A desert that already exists at the limits of survival becomes even less forgiving. And that dependence on distant forces is about to reveal the greatest vulnerability of all, because the most dangerous threat facing the Atacama today is not actually located inside the desert. The forces shaping the Atacama begin thousands of miles from the desert itself. While the landscape is often described as isolated, it is actually connected to some of the largest climate systems on the planet. A slight shift in ocean temperatures across the equatorial Pacific can eventually influence rainfall in northern Chile. Changes in snowfall across the Andes can alter water supplies months later. Even atmospheric circulation over Antarctica can affect weather patterns reaching South America. The Atacama survives within a network so vast that many of the events determining its future occur far beyond its horizon. One of the clearest examples appears during El Niño years. As Pacific Ocean temperatures rise, weather patterns across western South America can change dramatically. Regions that normally receive almost no precipitation may suddenly experience rare storms. Rivers that remain dry for years can briefly begin flowing again. Desert valleys may show bursts of vegetation that seem almost impossible after years of complete drought. For a short time, the landscape appears transformed. Then the transformation reveals another hidden danger. The Atacama is so dry that many slopes have little vegetation to stabilize loose sediment. When unusually heavy rainfall finally arrives, the ground often cannot absorb water efficiently. Instead, floodwaters race through narrow valleys carrying rocks, mud, and debris. Communities built around normally dry riverbeds have repeatedly faced destructive flash floods after exceptionally rare storms. Infrastructure designed for years of drought suddenly confronts enormous volumes of moving water. In most climates, rain signals relief. Here, it can become one of the greatest hazards. The same desert famous for lacking water can experience devastating floods precisely because water arrives so infrequently. That contradiction has shaped both engineering and settlement across northern Chile. Roads crossing dry channels may remain untouched for years before a single storm washes away bridges and sections of highway within hours. Mining operations must prepare not only for prolonged drought, but also for rare weather events capable of interrupting transportation and damaging critical infrastructure. These extremes expose another reality. The Atacama does not reward stability. It demands preparation for conditions that may occur only once in decades. This unpredictability has become increasingly important as global demand for critical minerals continues growing. Lithium, copper, and other resources extracted from northern Chile move through international supply chains that manufacturers often assume will remain reliable. Yet nearly every shipment begins its journey across a landscape vulnerable to disruptions from weather, earthquakes, and limited water availability. Earthquakes introduce another layer of risk that is easy to overlook. Northern Chile lies along one of the most active tectonic boundaries on Earth, where the Nazca Plate slowly descends beneath the South American Plate. This process has produced some of the strongest earthquakes ever recorded, including the magnitude 9.5 Valdivia earthquake in 1960 farther south, still the largest instrumentally recorded earthquake in history. Although that event occurred well beyond the Atacama, the same tectonic system extends beneath the region. Mining facilities, highways, ports, pipelines, and observatories all operate with the knowledge that powerful seismic events are inevitable. The desert itself appears motionless. The ground beneath it is anything but. Every major investment in the Atacama depends not only on surviving extreme aridity, but also on engineering structures capable of withstanding violent geological forces. Few places combine so many environmental challenges in one location. Extreme dryness, scarce water, intense solar radiation, high altitude, seismic activity, and long supply routes all intersect within the same region. Remove any one of those pressures, and life becomes easier. Together they create one of the most demanding environments where modern industry continues to expand. That expansion raises a much larger question. If one of the harshest places on Earth has become indispensable to the technologies shaping the future, what happens when the limits of the desert itself begin pushing back? For thousands of years, people learned to survive in the Atacama by accepting one simple rule. They never tried to conquer the desert. They adapted to it. Indigenous communities, such as the Atacameño, also known as the Licanantay, established settlements only where dependable water existed. Villages appeared beside springs, streams fed by mountain snowmelt, and small, fertile valleys where crops could survive despite the surrounding emptiness. Every decision from agriculture to trade routes reflected an understanding that water was not simply a resource. It was the foundation upon which every other activity depended. That principle remains true today. Modern technology has changed how minerals are extracted, how roads are built, and how communications reach remote regions, but it has not changed the desert itself. Every industrial operation still begins with the same question that guided ancient settlements. Where will the water come from? In recent decades, some mining companies have invested billions of dollars to reduce dependence on freshwater aquifers. Instead of pumping groundwater from inland basins, desalination plants have been constructed along Chile's Pacific coast. These facilities remove salt from seawater before sending fresh water through pipelines that climb thousands of feet into the Andes and across the desert toward mining operations. The engineering involved is extraordinary. Some pipelines transport water more than 100 miles while overcoming massive elevation changes. Powerful pumping stations operate continuously to move water uphill through one of the most difficult environments on Earth. Every gallon delivered inland represents an enormous investment in energy, infrastructure, and maintenance. The desert has forced humanity to reverse one of nature's oldest rules. Instead of rivers flowing from mountains to the sea, machines now push water from the sea back toward the mountains. That hidden network rarely appears in photographs of the Atacama. Visitors see salt flats, volcanoes, and endless rocky plains. They do not see the pipelines buried beneath the ground or the electrical systems that keep water moving every hour of every day. Without those systems, much of the modern economy operating inside the desert would slow dramatically. The Atacama teaches the same lesson again and again. The visible landscape tells only a small part of the story. Its survival depends on infrastructure hidden from view. The same pattern extends into transportation. Many roads crossing the desert seem almost perfectly straight, disappearing into the horizon with no towns for dozens of miles. Those routes support an enormous flow of copper, lithium, industrial equipment, fuel, food supplies, and construction materials. Drivers often spend hours without encountering another settlement. Mechanical failures become far more serious than they would elsewhere because assistance may be many miles away. Vehicle preparation is treated as a safety requirement rather than a convenience. Fuel, spare tires, communication equipment, and emergency water supplies are considered essential before entering remote sections of the desert. The environment offers almost no margin for error. A minor problem that would be inconvenient in another region can become life-threatening under the intense sun, low humidity, and vast distances separating population centers. Search and rescue teams operating in northern Chile understand these risks well. Modern satellite communication and GPS technology have significantly improved emergency response, yet locating stranded travelers can still be difficult across an immense landscape where roads stretch through terrain that changes very little for hundreds of square miles. Distances become deceptive. Mountains that appear close may require hours to reach. Heat during the day accelerates dehydration, while nighttime temperatures at higher elevations can fall sharply. The desert constantly reminds anyone entering it that appearances cannot be trusted. A destination that seems nearby may remain out of reach far longer than expected. A dry valley may suddenly carry floodwater after a distant storm. A place that appears completely lifeless may support one of the world's most valuable ecosystems beneath its surface. And nowhere is that contradiction more dramatic than in the strange moments when the deadliest desert on Earth briefly transforms into a landscape covered with flowers. In most years, the Atacama appears permanently locked in shades of brown, gray, and white. Satellite images show an immense landscape of salt flats, volcanic peaks, rocky plateaus, and dry valleys stretching toward the Pacific Ocean. Nothing about those images suggests that millions of flowers are waiting just beneath the surface. Yet every few years, under a precise combination of climatic conditions, one of the rarest natural events on Earth unfolds across parts of the desert. It is known as the Desierto Florido, the flowering desert. The transformation begins with rain, not the brief showers common in temperate climates, but unusually heavy precipitation linked to stronger than normal El Niño conditions. Water soaks into ground that has remained dry for years, sometimes even decades. Hidden beneath the soil are seeds that have survived extraordinary periods of dormancy. They are not dead, they are waiting. Within days, the first green shoots appear. Soon afterward, entire hillsides erupt with purple, yellow, white, and pink blossoms stretching across landscapes that previously seemed incapable of supporting any vegetation at all. The contrast is almost unbelievable. Scientists have documented more than 200 plant species associated with these flowering events, many of which are specially adapted to complete their entire life cycle within a remarkably short period. Germination, flowering, pollination, seed production, and dormancy all occur rapidly before moisture disappears once again. Timing is everything. A delayed bloom or an extended dry period can dramatically reduce reproductive success. The flowers are not an exception to the desert's rules. They are another example of organisms perfectly adapted to them. For insects, birds, and small mammals, these brief flowering seasons create temporary explosions of food and activity. Species that remain difficult to observe during ordinary years suddenly become much more visible. Pollinators emerge in large numbers. Birds migrate through blooming valleys. Even scientists often adjust research schedules to document ecological changes that may last only a few weeks before the landscape returns to silence. Then, almost as quickly as it appeared, the spectacle disappears. The plants wither, the seeds fall. The desert resumes its familiar appearance, hiding the next generation beneath the soil until conditions align once again. What seems like a miracle is actually a carefully evolved survival strategy refined over thousands of years. But not every rare event in the Atacama brings life. Some arrive from space. The desert's exceptional dryness has preserved meteorites better than almost anywhere else on Earth. Across its vast surface, researchers have recovered thousands of extraterrestrial rocks, many remaining remarkably well preserved because moisture-driven weathering is so limited. Some meteorites have rested undisturbed for tens of thousands of years, creating one of the richest natural collections of space debris found anywhere on the planet. Among the most famous discoveries is the Monteraqui impact crater, formed thousands of years ago when a massive iron meteorite struck the desert at tremendous speed. Although erosion has softened its appearance over time, the crater remains one of the clearest reminders that the Atacama records events reaching far beyond Earth's atmosphere. Scientists value these meteorites not only because they are rare, but because they preserve information dating back to the formation of the solar system more than 4.5 billion years ago. The desert has become a natural archive. It stores evidence of ancient climates, human civilizations, mining booms, biological survival, and even fragments of worlds that existed before Earth itself was fully formed. Very few places preserve history across such enormous spans of time. Yet, despite everything researchers have learned, the Atacama continues revealing new discoveries. Hidden caves, ancient caravan routes, previously unknown microbial communities, and archaeological sites continue to emerge from a landscape that still appears almost empty to the casual observer. The deadliest desert on Earth has never been truly empty. It has simply concealed its secrets better than almost anywhere else. Perhaps the greatest misconception about the Atacama is that its danger comes only from thirst. Lack of water has certainly claimed lives throughout history, but the desert's true threat is far more deceptive. It removes every margin for error. A navigational mistake, a mechanical failure, a sudden change in weather, or a simple miscalculation of distance can rapidly become a survival emergency. In many environments, people can adapt after making a mistake. In the Atacama, there is often no second chance. Rescue may be hours away, temperatures may exceed 100 degrees Fahrenheit during the afternoon, humidity remains exceptionally low, and shade is almost non-existent across vast stretches of open terrain. Even experienced travelers prepare with extraordinary caution. Modern expeditions carry satellite communication devices because cellular coverage disappears across many remote areas. Vehicles often travel in pairs to reduce the risk of becoming stranded. Water reserves are calculated well beyond expected consumption. Spare fuel, emergency shelters, recovery equipment, and medical supplies are considered essential rather than optional. These precautions are not signs of fear. They reflect an understanding earned through generations of experience. The desert punishes confidence more quickly than inexperience. Those who underestimate it often become its most vulnerable visitors. This pattern has repeated throughout history. Prospectors searching for mineral deposits sometimes disappeared after venturing too far from reliable water sources. Drivers have become stranded after underestimating distances between settlements. Climbers attempting nearby volcanoes have encountered altitude sickness long before reaching their objectives. At elevations exceeding 15,000 feet, oxygen levels fall dramatically. The combination of intense ultraviolet radiation, thin air, freezing nighttime temperatures, and daytime heat creates physiological stress unlike almost anywhere else on Earth. Many visitors expect the greatest challenge to be heat. Instead, they discover that elevation becomes the more immediate obstacle. Several of the Atacama's surrounding volcanoes rise above 18,000 feet. Scientific observatories, mining facilities, and research stations often operate at altitudes where acclimatization becomes necessary. Workers follow carefully planned rotation schedules because prolonged exposure can affect sleep, concentration, and cardiovascular performance. Modern medicine has made these operations possible, but it has not removed the environmental limits imposed by high altitude. The desert constantly reminds people that technology can reduce risk without eliminating it. This reality became even more apparent during one of the most remarkable rescue operations in modern history. In 2010, the collapse of the San Jose copper and gold mine trapped 33 miners nearly half a mile beneath the Atacama Desert. For 17 days, no one knew whether they had survived. Families gathered outside the mine while rescue teams drilled through solid rock searching for any sign of life. The surrounding desert once again demonstrated its unforgiving nature. The same geological formations that contained valuable mineral deposits also created one of the most difficult rescue environments imaginable. Then, an extraordinary message reached the surface. Attached to the drill was a handwritten note. It contained only a few words. "We are well in the shelter, the 33 of us." That single sentence transformed what many believed was a recovery mission into one of the most ambitious rescue efforts ever attempted. Engineers from multiple countries worked together to design specialized drilling systems capable of reaching the trapped miners without triggering additional collapses. After 69 days underground, every miner was brought safely to the surface. The rescue became international news. Yet it also highlighted something much larger than human determination. The Atacama still holds enormous power over every person who enters it. Even with modern engineering, advanced communication systems, satellite mapping, and global cooperation, one accident beneath this desert required months of planning, unprecedented coordination, and extraordinary precision to overcome. That story illustrates the central truth of the Atacama. Humanity has learned to work within the desert. It has never truly mastered it. And as the climate continues changing across the planet, scientists are beginning to ask whether the Atacama itself may become the first place to reveal just how fragile that relationship really is. Today, the Atacama stands at the center of a paradox unlike any it has faced before. For centuries, people crossed the desert to extract what lay beneath its surface. Now the world depends on those resources to build technologies intended to reduce humanity's environmental impact. Electric vehicles, renewable energy storage systems, advanced electronics, and power infrastructure all require materials produced in enormous quantities, and northern Chile supplies a significant share of several of them. The future of clean energy is increasingly connected to one of the harshest landscapes on Earth. Yet that growing demand also places greater pressure on the fragile systems that have allowed life to exist there for thousands of years. Scientists continue studying how groundwater responds to both natural climate cycles and industrial extraction. Although surface conditions appear almost unchanged from year to year, underground reservoirs evolve slowly over long periods. Water entering an aquifer today may have begun its journey decades or even centuries earlier, as snow falling high in the Andes. Once that water is removed faster than it can be naturally replenished, recovery may require generations rather than seasons. The consequences are not always immediately visible. A lagoon may shrink only slightly. A wetland may lose a small portion of its vegetation. A flamingo population may decline gradually over several breeding cycles. Each individual change can appear insignificant. Together, they reveal how delicate the desert's balance has always been. This slow pace makes environmental monitoring especially difficult. Unlike disasters that unfold within hours, ecological changes in the Atacama often develop over many years. Researchers compare satellite imagery, groundwater measurements, wildlife surveys, and long-term climate records to understand trends that would otherwise remain invisible. In many ways, studying the Atacama requires patience measured not in weeks, but in decades. That perspective also changes how scientists define survival. The desert has endured volcanic eruptions, earthquakes, dramatic climate shifts, and millions of years of geological change. It will almost certainly outlast every mine, every highway, and every observatory built within it. The real question is not whether the Atacama will survive. It is whether the ecosystems and human activities that now depend upon it can remain sustainable as environmental pressures continue to grow. The desert itself is unlikely to disappear. Its hidden sources of life could. That distinction has become increasingly important for researchers around the world because the Atacama is more than a regional landscape. It serves as a natural laboratory helping scientists prepare for challenges far beyond Chile. Climate researchers study long-term drought. Geologists examine tectonic processes. Biologists investigate the limits of microbial survival. Astronomers explore the origins of galaxies through skies almost completely free of atmospheric interference. Engineers test technologies designed for future planetary exploration. Few places contribute to so many scientific fields at the same time. Each discovery made in the Atacama expands knowledge reaching well beyond the desert's borders. Perhaps that is why the landscape continues capturing human imagination despite its apparent emptiness. At first glance, it seems almost featureless, but every layer reveals another story. Ancient trade routes crossing impossible distances. Ghost towns left behind by vanished industries. Salt flats concealing strategic minerals. Volcanoes towering above one of Earth's driest climates. rare flowers blooming after years of silence, microscopic organisms surviving where life was once believed impossible, telescopes looking billions of years into the past from mountains that receive almost no rain. The Atacama has never been defined by what it lacks. It has always been defined by what manages to endure, and that may be its greatest lesson. The deadliest desert on Earth is not simply a place where survival is difficult. It is a place where every form of survival, from ancient civilizations to microscopic life, exists because it has adapted to some of the most unforgiving conditions our planet can create. That quiet struggle, unfolding across millions of years, is what transformed an empty-looking landscape into one of the most extraordinary places on Earth.